universe began approximately 13.8 billion years ago in an event known as the Big Bang, which marks the origin of space, time, matter, and energy. Contrary to common intuition, the Big Bang was not an explosion occurring at a single point in pre-existing space. Rather, it was the rapid expansion of space itself from an extremely hot, dense initial state. At the earliest measurable moment, known as the Planck time, around 10 seconds after the beginning, the universe was governed by quantum gravitational effects, and the known laws of physics cannot yet fully describe conditions at that scale. As the universe expanded, it cooled rapidly. Within fractions of a second, fundamental forces that were initially unified began to separate into the distinct interactions observed today. Gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Elementary particles such as quarks, leptons, and gauge bosons emerged from high-energy radiation. During the first few minutes, protons and neutrons combined through nuclear reactions in a process called primordial nucleosynthesis, forming the lightest elements, primarily hydrogen, helium, and trace amounts of lithium. Heavier elements could not form at this stage due to insufficient density and time. Roughly 380,000 years after the beginning, the universe cooled enough for electrons to combine with atomic nuclei, forming neutral atoms in an event known as recombination. This decoupled matter from radiation, allowing photons to travel freely through space for the first time. These photons persist today as the cosmic microwave background radiation, a nearly uniform thermal glow observed in all directions, providing strong observational evidence for the Big Bang model and precise information about the early universe's composition, geometry, and age. After recombination, the universe entered a prolonged period often called the Cosmic Dark Ages. During this time, matter was distributed almost uniformly, with tiny density fluctuations left over from earlier quantum irregularities. Under the influence of gravity, these fluctuations slowly grew, pulling matter into increasingly dense regions. Hundreds of millions of years later, the first stars ignited, ending the Dark Ages and initiating the process of cosmic reionization. These early stars were massive, short-lived, and composed almost entirely of hydrogen and helium, producing the first heavy elements through nuclear fusion and supernova explosions. The formation of stars led to the assembly of galaxies, which became the fundamental building blocks of large-scale cosmic structure. Over billions of years, galaxies merged, evolved, and organized themselves into clusters, filaments, and vast voids, forming the large-scale structure of the universe observed today. Throughout this expansion, space itself continued to stretch, carrying galaxies away from one another. Observations of distant galaxies show that the universe is not only expanding, but doing so at an accelerating rate, a phenomenon attributed to dark energy, an unknown form of energy that dominates the total energy budget of the cosmos. The Big Bang theory is supported by multiple independent lines of evidence. The expansion of space measured through galactic redshifts, the abundance of light elements predicted by early universe nuclear physics, and the detailed structure of the cosmic microwave background. Together, these observations form a coherent and predictive framework that explains how the universe evolved from a nearly uniform, ultra-hot beginning into a complex system filled with stars, galaxies, planets, and the physical conditions necessary for chemistry and life. While the Big Bang theory successfully describes the evolution of the universe from its earliest observable moments onward, it does not yet explain what, if anything, preceded the initial expansion, or why the universe began in such a low-entropy, highly ordered state. These questions lie at the frontier of modern cosmology, connecting observational astronomy with particle physics, quantum theory, and attempts to develop a complete theory of quantum gravity. After the universe emerged from its initial hot, dense state, its most defining property became continuous expansion. This expansion is not the motion of galaxies through space, but the stretching of space itself, increasing the distance between all unbound cosmic structures. The observational foundation for this idea comes from the systematic redshift of light emitted by distant galaxies. The farther a galaxy is, the faster it appears to be receding. This relationship, first quantified in the early 20th century, demonstrates that the universe has been expanding for most of its history and was denser and hotter in the past. In the earliest fraction of a second, expansion occurred at an extraordinary rate during a phase known as cosmic inflation. Inflation proposes that space expanded exponentially for a very brief period, possibly between 10.3 and 10.32 seconds after the beginning. During this interval, regions of space that were once subatomic in size were stretched to macroscopic scales. Inflation explains several otherwise puzzling properties of the universe, including its large-scale uniformity, geometric flatness, and the absence of exotic relics predicted by certain high-energy theories. One of the strongest motivations for inflation is the observed uniform temperature of the cosmic microwave background across vast regions of the sky. Without inflation, widely separated regions would never have been in causal contact and therefore could not have reached the same physical conditions. Inflation solves this horizon problem by positing that these regions were once close together before being rapidly driven apart. Similarly, inflation explains why the universe appears spatially flat, meaning that Euclidean geometry holds on the largest observable scales. Rapid expansion would dilute any initial curvature, much as inflating a balloon makes its surface appear flatter to a small observer. Quantum mechanics plays a central role in inflationary theory. Tiny quantum fluctuations in energy density, amplified by rapid expansion, became the seeds of all later cosmic structure. These fluctuations introduced minute variations in matter density that later grew under gravity into galaxies, clusters, and the large-scale filamentary network observed today. The statistical properties of these fluctuations, measured with high precision in the cosmic microwave background, closely match predictions made by simple inflationary models. After inflation ended, the universe continued expanding, but at a much slower rate governed primarily by its matter and radiation content. For billions of years, gravity acted to slow expansion as matter attempted to pull space back together. However, observations of distant supernovae revealed that expansion began accelerating again several billion years ago. This late-time acceleration is attributed to dark energy, a pervasive form of energy associated with space itself that exerts a repulsive gravitational effect. As space expands, dark energy does not dilute in the same way as matter or radiation, allowing it to dominate the universe's dynamics over time. The expansion rate of the universe is described by a time-dependent parameter that reflects how fast distances between cosmic objects grow. Measurements of this rate using different observational methods, such as galaxy motions, cosmic background radiation, and supernova brightness, have revealed subtle tensions that may point to new physics beyond the standard cosmological model. Whether these discrepancies indicate unknown systematic effects or fundamental gaps in understanding remains an open question. Inflation and expansion together form a continuous narrative of cosmic evolution, an early burst of extreme growth that set the initial conditions, followed by a long period of structured expansion shaped by matter, radiation, and dark energy. While inflation is strongly supported by observational evidence, the exact physical mechanism driving it is still unknown. Determining the nature of the field or process responsible for inflation is one of the central goals of modern cosmology, linking the behavior of the largest structures in the universe to the smallest scales described by fundamental physics. All physical interactions in the universe are governed by a small set of fundamental forces that determine how matter and energy behave across every scale, from subatomic particles to galaxies. Modern physics identifies four such forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. These forces are not arbitrary. They arise from underlying symmetries of nature and are mediated by fundamental particles known as force carriers. Together, they define the structure, stability, and evolution of everything in space. Gravity is the weakest of the four forces, yet it dominates cosmic behavior because it is always attractive and acts over infinite range. It governs the motion of planets, stars, galaxies, and the large-scale structure of the universe. Gravity is described classically by general relativity, which interprets it not as a force in the traditional sense, but as the curvature of spacetime caused by mass and energy. Despite its success on large scales, gravity has not yet been fully reconciled with quantum mechanics, making it the least understood force at the most fundamental level. Electromagnetism governs interactions between electrically charged particles and is responsible for light, chemistry, and the structure of atoms and molecules. It operates over infinite range and is vastly stronger than gravity at microscopic scales. Electromagnetic interactions are mediated by photons, which are massless particles that also carry electromagnetic radiation. Nearly all everyday phenomena, from solid matter to biological processes, depend on electromagnetic forces. Yet on cosmic scales, it plays a secondary role compared to gravity, because most large structures are electrically neutral. The strong nuclear force is responsible for binding quarks together to form protons and neutrons, and for holding atomic nuclei together. It is the strongest of all known forces, but acts only over extremely short distances, comparable to the size of an atomic nucleus. This force is mediated by particles called gluons, which bind quarks through an interaction described by quantum chromodynamics. Without the strong force, atomic nuclei would not exist, and the universe would lack the stable matter required for stars, planets, and life. The weak nuclear force governs processes that change one type of particle into another, such as radioactive decay and nuclear fusion reactions in stars. Although weaker than electromagnetism and the strong force, it plays a critical role in stellar evolution and element formation. The weak force is mediated by heavy particles known as W and Z bosons, which limit its range to extremely short distances. Its behavior violates certain symmetries, such as parity, making it unique among the fundamental interactions. All matter in the universe is composed of elementary particles that are not known to have internal structure. These particles fall into two main categories: fermions, which make up matter, and bosons, which mediate forces. Fermions include quarks and leptons. Quarks combine to form protons and neutrons, while leptons include electrons and neutrinos. Bosons include photons, gluons, W and Z bosons, and the Higgs boson, which is associated with the mechanism that gives particles mass. The Higgs field permeates all of space, and particles interacting with it acquire mass. This mechanism explains why some particles are massive while others, like photons, remain massless. Without this process, matter would not clump into stable structures, and the universe would be radically different. Neutrinos, nearly massless and weakly interacting, are among the most abundant particles in space and play subtle but important roles in cosmic evolution. At extremely high energies, such as those present in the earliest moments of the universe, these forces are thought to unify, behaving as a single interaction. As the universe expanded and cooled, symmetry breaking caused the forces to separate into the distinct forms observed today. Understanding this unification remains a central goal of fundamental physics, linking cosmology with particle theory and offering insight into the deepest laws governing space and existence. A large fraction of the universe is composed of substances that cannot be directly seen or detected through electromagnetic radiation, yet their presence is inferred through their gravitational effects. These components are known as dark matter and dark energy, and together they dominate the total mass energy content of the cosmos. Ordinary matter, atoms, stars, planets, gas, and dust, accounts for only a small minority of what exists. Understanding these invisible components is essential to explaining how the universe formed, evolved, and continues to change. Dark matter is a form of matter that does not emit, absorb, or reflect light, making it invisible to telescopes across the electromagnetic spectrum. Its existence was first inferred from the motion of stars in galaxies. Stars orbit galactic centers at speeds that cannot be explained by the gravitational pull of visible matter alone. According to classical physics, outer stars should move more slowly than inner ones, yet observations show that rotation speeds remain nearly constant with distance. This behavior indicates the presence of a large amount of unseen mass surrounding galaxies in extended halos. Additional evidence for dark matter comes from galaxy clusters, gravitational lensing, and the cosmic microwave background. In clusters, galaxies move too rapidly to be held together by visible mass alone. Gravitational lensing, where light from distant objects is bent by gravity, reveals mass distributions that far exceed what can be accounted for by luminous matter. Precise measurements of early universe radiation patterns also require dark matter to explain how small density fluctuations grew into galaxies within the available time. Dark matter interacts primarily through gravity and possibly through the weak nuclear force, but not through electromagnetism. This means it does not clump into stars or planets and does not dissipate energy through radiation. Several theoretical candidates have been proposed, including weakly interacting massive particles, axions, and other exotic particles, beyond the current standard model of particle physics. Despite decades of experimental effort, dark matter has not yet been directly detected in laboratory experiments, making its true nature one of the most significant open problems in science. Dark energy is an even more mysterious component, responsible for the accelerated expansion of the universe. Observations of distant supernovae show that the expansion rate of the universe has been increasing for the last several billion years. This acceleration cannot be explained by matter or radiation, both of which slow expansion through gravity. Instead, dark energy appears to exert a repulsive effect, counteracting gravitational attraction on the largest scales. Unlike dark matter, which clumps around galaxies and clusters, dark energy appears to be uniformly distributed throughout space. Its density remains nearly constant even as the universe expands, meaning that as space grows, the total amount of dark energy increases. The simplest explanation for dark energy is the cosmological constant, a property of space itself that produces a constant energy density. However, theoretical predictions of vacuum energy from quantum physics differ from observed values by an enormous margin, indicating a profound gap in understanding. Dark energy does not significantly affect small-scale structures like galaxies or solar systems, but it dominates the behavior of the universe on the largest scales. As expansion accelerates, distant galaxies move beyond observable horizons, eventually becoming unreachable even in principle. Over extremely long timescales, this process may isolate gravitationally bound systems from one another, fundamentally altering the observable universe. Together, dark matter and dark energy shape cosmic evolution. Dark matter provides the gravitational scaffolding necessary for galaxies and large-scale structures to form, while dark energy controls the long-term fate of cosmic expansion. Although their effects are clearly measured, their underlying nature remains unknown, representing one of the deepest and most consequential challenges in modern physics and cosmology. Galaxies are vast, gravitationally bound systems composed of stars, gas, dust, dark matter, and stellar remnants, and they represent the fundamental structural units of the visible universe. Their formation began several 100 million years after the universe's birth, when small density fluctuations in matter grew under gravity. Dark matter played a decisive role in this process by collapsing first into large, invisible halos. Ordinary matter fell into these halos, cooled and condensed, eventually igniting star formation and giving rise to the first proto-galaxies. The earliest galaxies were small, irregular, and intensely active. They formed stars at extremely high rates and contained little chemical diversity, since heavy elements had not yet been widely produced. As stars lived and died, supernova explosions enriched surrounding gas with heavier elements, enabling more complex chemistry and influencing subsequent generations of stars. Over billions of years, galaxies evolved through continuous star formation, gas accretion from intergalactic space, and frequent mergers with other galaxies. Galaxy formation is a hierarchical process. Small galaxies formed first and gradually merged to create larger systems. Major mergers, involving galaxies of comparable size, can dramatically alter structure, triggering bursts of star formation and reshaping stellar orbits. Minor mergers, in which a large galaxy absorbs much smaller companions, contribute stars and gas while slowly building mass. These interactions are common and have played a central role in shaping present-day galaxies. Galaxies are classified primarily by their shape and structure. Spiral galaxies are characterized by flattened rotating disks with spiral arms extending outward from a central bulge. These arms are rich in gas and dust and are sites of active star formation, producing many young, bright stars. Spiral galaxies also contain older stars in their bulges and halos. Their organized rotation reflects the conservation of angular momentum during formation. Elliptical galaxies have smooth, rounded shapes ranging from nearly spherical to highly elongated. They contain little cold gas or dust and show minimal ongoing star formation. Most of their stars are old and formed early in cosmic history. Elliptical galaxies are commonly found in dense environments such as galaxy clusters, and are often the result of repeated mergers that randomize stellar motions and eliminate disk structures. Irregular galaxies lack a defined shape and often appear chaotic. Many are small and rich in gas, with active star formation driven by gravitational interactions or internal turbulence. Some irregular galaxies are primordial in nature, while others are distorted remnants of past encounters. Their diversity reflects the wide range of physical processes influencing galactic evolution. Beyond visible matter, galaxies are dominated by dark matter, which forms extended halos surrounding their luminous components. These halos contain most of a galaxy's mass and control its rotation and stability. Without dark matter, galaxies could not maintain their observed structures or survive over cosmic timescales. The distribution of dark matter also governs how galaxies cluster and interact on large scales. Galaxies are not isolated objects. They exist within a cosmic network of filaments and clusters shaped by gravity. Environmental factors strongly influence their evolution. Galaxies in dense regions tend to lose gas through interactions and become passive, while isolated galaxies can continue forming stars for much longer periods. Over cosmic time, this interplay between internal processes and external environment has produced the immense diversity of galaxies observed today. Modern observations across multiple wavelengths reveal galaxies at different stages of evolution, allowing reconstruction of their life cycles. From faint early systems in the distant universe to massive mature galaxies nearby, these observations confirm that galaxies are dynamic, evolving structures shaped by gravity, matter, energy, and time. The Milky Way is a massive barred spiral galaxy that contains the solar system and hundreds of billions of stars, along with gas, dust, stellar remnants, and an extensive halo of dark matter. It formed over more than 13 billion years through the gradual collapse of matter, accretion of gas, and repeated mergers with smaller galaxies. Its present structure reflects a long history of rotation, star formation, and gravitational interaction within the evolving universe. The Milky Way has a flattened disk approximately 100,000 light-years in diameter and about 1,000 light-years thick in its stellar component. This disk contains spiral arms that wind outward from the central region. These arms are not rigid structures, but density waves, regions where gas is compressed as it orbits the galactic center. This compression triggers star formation, making spiral arms rich in young, massive, and luminous stars, as well as nebulae composed of gas and dust. At the center of the galaxy lies a dense bulge of older stars and a compact region known as the galactic nucleus. Embedded within this nucleus is a supermassive black hole with a mass of several million times that of the Sun. Although currently relatively inactive, this black hole exerts strong gravitational influence on nearby stars and gas, and likely played a more energetic role earlier in the galaxy's history. The bulge itself contains little cold gas and exhibits minimal ongoing star formation, indicating that its stellar population formed early. Surrounding the disk and bulge is the galactic halo, a vast, roughly spherical region extending far beyond the visible galaxy. The halo contains old stars, globular clusters, and most of the galaxy's dark matter. Globular clusters are tightly bound collections of hundreds of thousands of ancient stars, among the oldest objects in the galaxy. Their distribution and composition provide critical clues about the Milky Way's early formation and merger history. The Milky Way rotates differentially, meaning stars closer to the center orbit faster than those farther out. One complete orbit of the Sun around the galactic center takes about 225–250 million years, a period known as a galactic year. The Sun resides in the disk, within a minor spiral feature between two major arms, at a distance of roughly 26,000 light-years from the galactic center. From this position, observations of the galaxy are complicated by dust and gas that obscure direct lines of sight, requiring radio, infrared, and other non-visible wavelengths to map its structure accurately. Chemical composition within the Milky Way varies with location. The inner regions are richer in heavy elements due to intense early star formation and repeated recycling of stellar material. The outer disk and halo contain stars with lower metal content, reflecting formation at earlier times or from less enriched gas. This gradient records the galaxy's star formation history and the flow of matter over billions of years. The Milky Way continues to evolve. It is actively forming new stars, accreting gas from its surroundings, and interacting gravitationally with nearby satellite galaxies. These interactions stretch stars into streams and slowly alter the galaxy's mass and structure. Far in the future, continued mergers and internal processes will further reshape the galaxy, demonstrating that even large, seemingly stable systems are dynamic products of cosmic time. Galaxy clusters are the largest gravitationally bound structures in the universe, consisting of hundreds to thousands of galaxies embedded within vast reservoirs of hot gas and dominated by dark matter. They formed from the highest density regions of the early universe, where gravity was strong enough to draw matter together on enormous scales. Over billions of years, smaller galaxy groups merged and accreted into progressively larger systems, producing the massive clusters observed today. The mass of a typical galaxy cluster is overwhelmingly dominated by dark matter, which provides the gravitational framework that holds the system together. Ordinary matter makes up a smaller fraction, with galaxies contributing only a minor portion of the total mass. A significant amount of baryonic matter exists as extremely hot, diffuse gas filling the space between galaxies. This intracluster gas reaches temperatures of tens of millions of degrees due to gravitational compression and emits strongly in X-rays, making galaxy clusters prominent X-ray sources. Galaxies within clusters experience environments very different from isolated galaxies. high relative velocities, strong tidal forces, and interactions with hot intracluster gas strip galaxies of their own gas, suppressing star formation over time. As a result, clusters are dominated by elliptical and lenticular galaxies containing older stellar populations, while gas-rich spiral galaxies are more common in lower-density environments. This environmental transformation is a key driver of galactic evolution. Clusters are not randomly distributed in space. They form nodes within a vast cosmic network where filaments of galaxies and dark matter intersect. On scales larger than clusters lie superclusters, enormous associations of clusters and galaxy groups spanning hundreds of millions of light years. Unlike clusters, superclusters are not fully gravitationally bound structures. Instead, they are transient features shaped by the initial conditions of the universe and ongoing cosmic expansion. One of the most studied nearby clusters is the Virgo cluster, which contains thousands of galaxies and plays a dominant role in the dynamics of the local universe. The Milky Way itself lies on the outskirts of this cluster, influenced by its gravitational pull. Observations of the Virgo cluster provide crucial insights into cluster structure, galaxy interactions, and the distribution of dark matter. On even larger scales, clusters and superclusters are organized into immense regions defined by coherent galaxy motions. The Milky Way is part of a vast supercluster region known as Laniakea supercluster, which spans more than 500 million light years and contains tens of thousands of galaxies. This structure is defined not just by spatial distribution, but by the flow of galaxies toward a common gravitational basin, illustrating how gravity shapes cosmic organization across extreme distances. The study of galaxy clusters provides powerful tests of cosmological models. The number, mass distribution, and evolution of clusters over time are highly sensitive to fundamental properties of the universe, including the amount of dark matter and the behavior of dark energy. By observing clusters at different distances, astronomers reconstruct how structure grew from early density fluctuations into today's complex cosmic web. Clusters also act as natural gravitational lenses. Their immense mass bands space them strongly enough to distort and magnify the light of background galaxies. These lensing effects allow precise mapping of dark matter distributions independent of visible matter, offering some of the clearest evidence for dark matter's existence and behavior. Together, galaxy clusters and superclusters represent the upper levels of cosmic structure. They trace the imprint of initial conditions from the early universe, reveal the dominance of dark matter, and provide critical constraints on cosmic evolution. Their existence demonstrates that the universe is structured hierarchically, with gravity organizing matter from the smallest scales of stars to the largest assemblies known. On the largest observable scales, matter in the universe is organized into a vast, interconnected network known as the cosmic web. This structure is composed of filaments, sheets, and nodes formed primarily by dark matter, with galaxies and galaxy clusters tracing these underlying gravitational scaffolds. Rather than being randomly distributed, galaxies occupy preferred regions where matter density is higher, while enormous voids, nearly empty regions, separate these structures. The cosmic web represents the ultimate outcome of gravitational growth, acting on tiny density fluctuations present in the early universe. The origin of the cosmic web lies in minute variations in density that arose shortly after the universe began. These variations were extremely small, differing from the average density by only 1 part in 100,000. As the universe expanded, gravity amplified these irregularities. Regions slightly denser than average attracted more matter, growing progressively denser over time, while underdense regions lost matter and expanded into voids. This contrast intensified over billions of years, producing the filamentary and cellular patterns observed today. Dark matter plays the dominant role in shaping large-scale structure. Because it does not interact with radiation, it began collapsing earlier than ordinary matter, forming extended filaments and halos. Baryonic matter fell into these dark matter potential wells, cooling and condensing into galaxies and clusters along the filaments. As a result, the visible universe closely follows the invisible architecture defined by dark matter, making galaxies effective tracers of the cosmic web. Filaments are the most striking components of this structure. They are elongated regions tens to hundreds of millions of light years long, containing chains of galaxies, gas, and dark matter. At the intersections of filaments lie dense nodes, where galaxy clusters form. These nodes represent the most massive bound structures in the universe. Surrounding the filaments are vast sheets and walls, thin but extensive regions that further connect the network. Between these features lie cosmic voids, enormous regions with very low galaxy density that can span hundreds of millions of light years. The cosmic web is not static. Matter continues to flow along filaments toward dense nodes, driven by gravity. Galaxies migrate through this network over cosmic time, often undergoing interactions and mergers as they move into denser environments. Gas streams along filaments also fuel star formation in galaxies, particularly in the early universe when accretion rates were high. This continuous flow of matter links large-scale structure directly to galaxy evolution. Observational evidence for the cosmic web comes from large galaxy surveys that map the three-dimensional distribution of millions of galaxies. These surveys reveal striking patterns of filaments and voids consistent with predictions from cosmological simulations. Additional confirmation comes from observations of intergalactic gas detected through absorption features in the spectra of distant quasars, showing that filaments contain diffuse gas even where galaxies are sparse. The statistical properties of the cosmic web provide critical tests of cosmological models. The size, distribution, and connectivity of filaments depend sensitively on the amount of dark matter, the nature of dark energy, and the initial conditions of the universe. By comparing observations with simulations, scientists can constrain fundamental cosmological parameters and test theories of gravity on the largest scales. On the largest scales accessible to observation, the universe appears homogeneous and isotropic, meaning it looks statistically similar in all directions and locations. The cosmic web exists within this overall uniformity, representing structured variations embedded in an otherwise smooth expansion. This balance between order and uniformity is a defining feature of the universe. The cosmic web is the largest known structure formed by natural processes. It links the physics of the early universe with the distribution of galaxies today, demonstrating how simple physical laws operating over immense timescales produce complexity on the grandest scales imaginable. Stars are born within vast clouds of gas, and thus known as nebulae, which are primarily composed of hydrogen with smaller amounts of helium and trace heavier elements. These clouds exist throughout galaxies and can span dozens to hundreds of light years. Under normal conditions, internal pressure balances gravity and prevents collapse. Star formation begins when this balance is disturbed, often by external triggers such as shock waves from nearby supernova explosions, collisions between molecular clouds, or compression caused by spiral density waves in galactic disks. When a region within a nebula becomes dense enough, gravity causes it to contract. As the cloud fragment collapses, it breaks into smaller clumps, each with the potential to form a star. During collapse, gravitational potential energy is converted into thermal energy, raising the temperature of the core. Conservation of angular momentum causes the contracting material to spin faster, flattening into a rotating disk around a central dense object known as a protostar. This disk plays a crucial role in regulating mass accretion and in the eventual formation of planetary systems. As the protostar grows, it continues to accumulate mass from the surrounding envelope and disk. Powerful bipolar jets and stellar winds emerge along the rotation axis, expelling excess angular momentum and clearing surrounding material. These outflows are common in young stellar objects and can extend for several light years, influencing nearby regions of the nebula and sometimes triggering further star formation. The fate of a forming star is determined primarily by its mass. Low-mass protostars contract slowly, while high-mass protostars collapse rapidly and heat intensely. When the temperature in the core reaches approximately 10 million Kelvin, nuclear fusion ignites. Hydrogen nuclei begin fusing into helium, releasing enormous amounts of energy. This energy generates outward pressure that balances gravitational collapse, marking the moment the object becomes a true star. Star formation is inefficient. Only a small fraction of the mass of a molecular cloud ends up in stars, with the rest dispersed by radiation pressure, stellar winds, and supernova explosions. Massive stars, although rare, have a disproportionate impact on their environments. Their intense ultraviolet radiation ionizes surrounding gas, creating large glowing regions and halting further star formation nearby. Their short lifetimes end in supernova explosions that enrich the interstellar medium with heavy elements and reshape surrounding clouds. Stars rarely form in isolation. Most are born in clusters or associations containing dozens to millions of stars. These clusters range from loose groupings that disperse over time to tightly bound systems that persist for billions of years. The Sun itself likely formed in such a clustered environment. Interactions within clusters can influence stellar orbits, disk evolution, and the likelihood of planet formation. The initial distribution of stellar masses formed in a nebula follows a well-defined statistical pattern, with low-mass stars being far more common than massive ones. This distribution has profound implications for galactic evolution, chemical enrichment, and the long-term energy output of galaxies. Because low-mass stars burn fuel slowly, they dominate stellar populations over cosmic timescales. Star formation is an ongoing process throughout the universe. Observations of distant galaxies show that star formation rates were much higher billions of years ago, during a period when galaxies were rich in cold gas. Over time, gas supplies diminish and star formation slows. The cycle of star birth, evolution, and death continuously transforms galaxies, linking the small-scale physics of collapsing gas clouds to the large-scale history of the universe. Once a star ignites nuclear fusion in its core, it enters the longest and most stable phase of its life, known as the main sequence. During this stage, the star generates energy by fusing hydrogen into helium through nuclear reactions at its core. The energy released in these reactions produces outward pressure that balances the inward pull of gravity, creating a state of equilibrium that can last for millions to tens of billions of years, depending on the star's mass. The defining factor of a main sequence star is its mass. Mass determines core temperature, fusion rate, luminosity, size, and lifespan. Low-mass stars have relatively cool cores and burn hydrogen slowly, emitting modest amounts of energy. High-mass stars have extremely hot, dense cores where fusion proceeds rapidly, producing vast energy output but exhausting fuel much more quickly. As a result, massive stars are bright and short-lived, while small stars are dim but long-lived. Hydrogen fusion occurs primarily through two mechanisms. In lower-mass stars, fusion proceeds via a sequence of reactions that gradually combine protons into helium nuclei. This process is highly efficient at moderate temperatures and dominates in stars similar in size or smaller than the Sun. In more massive stars, a different fusion cycle becomes dominant, using existing carbon, nitrogen, and oxygen nuclei as catalysts to fuse hydrogen. This cycle is far more temperature sensitive and leads to much higher energy output. The balance between gravity and fusion-generated pressure is extremely delicate. If fusion rates increase slightly, the core heats up and expands, reducing density and slowing fusion back to equilibrium. If fusion slows, gravity compresses the core, raising temperature and restoring fusion. This self-regulating mechanism allows main sequence stars to remain stable for the majority of their lifetimes. Main sequence stars span a wide range of sizes and luminosities. At one extreme are red dwarfs, which are small, cool, and faint but extremely numerous. They can burn hydrogen for tens to hundreds of billions of years, far longer than the current age of the universe. At the other extreme are massive blue stars that shine intensely, but may leave the main sequence after only a few million years. Between these extremes lie stars of intermediate mass, including the Sun, with lifetimes of several billion years. The surface temperature of a main sequence star determines its color. Cooler stars emit more red and infrared light, while hotter stars emit more blue and ultraviolet radiation. This relationship between temperature, brightness, and mass produces a well-defined sequence when stars are plotted on a diagram comparing luminosity and temperature. This pattern reflects fundamental physical laws governing stellar structure and energy generation. Throughout the main sequence phase, stars gradually alter their internal composition. As hydrogen is converted into helium, the core becomes richer in helium and denser over time. Although the star appears stable from the outside, these slow internal changes eventually disrupt equilibrium. When hydrogen in the core is depleted, fusion can no longer sustain pressure against gravity, marking the end of the main sequence phase. Main sequence stars are the primary engines of energy production in galaxies. Their radiation illuminates interstellar space, drives chemical reactions, and supports planetary environments. Their steady output over long periods creates conditions under which planets can form, and in some cases, develop complex chemistry. Because most observable stars are in this stage, understanding main sequence behavior is central to understanding stellar populations, galactic evolution, and the physical conditions of the universe. After a star exhausts the hydrogen fuel in its core, the balance that maintained its stability is disrupted, initiating a profound transformation in structure and behavior. With no hydrogen fusion to counteract gravity, the core begins to contract under its own weight. As it compresses, temperature and pressure rise, while hydrogen fusion continues in a surrounding shell outside the core. The increased energy output from this shell causes the outer layers of the star to expand dramatically, and the star enters the giant phase of its life. For stars with low to intermediate mass, this expansion produces a red giant. These stars swell to many times their original size, sometimes engulfing nearby planets, while their surface temperatures decrease, giving them a reddish appearance. Inside the core, contraction continues until temperatures become high enough to ignite helium fusion. Helium nuclei begin fusing into heavier elements, releasing energy that temporarily stabilizes the star. This phase is relatively short compared to the long main sequence lifetime, but marks a critical transition in stellar evolution. As helium fuel is consumed, fusion becomes increasingly complex. In intermediate mass stars, helium fusion produces carbon and oxygen, but temperatures never become high enough to ignite further fusion stages. The star develops a layered internal structure with different fusion shells, while the outer envelope grows unstable. Eventually, the star sheds its outer layers into space through strong stellar winds, forming an expanding shell of gas enriched with heavy elements. The remaining core becomes a compact stellar remnant. This remnant, known as a white dwarf, is extremely dense and supported not by fusion, but by quantum mechanical pressure arising from tightly packed electrons. White dwarfs no longer generate energy and instead slowly cool over billions of years, radiating away stored heat. They represent the final evolutionary state of most stars in the universe, including those similar in mass to the Sun. In contrast, massive stars follow a far more violent evolutionary path. Their greater mass allows core temperatures to rise high enough to fuse progressively heavier elements. After hydrogen and helium, they burn carbon, neon, oxygen, and silicon in successive stages, each lasting progressively shorter periods. This process builds an onion-like structure of concentric shells, with the heaviest elements concentrated at the center. Fusion reactions continue until iron accumulates in the core. Iron fusion does not release energy. Instead, it consumes it. When an iron core grows beyond a critical mass, pressure can no longer resist gravitational collapse. In a fraction of a second, the core collapses catastrophically, triggering a supernova explosion. This explosion releases more energy than the star emitted during its entire lifetime and ejects vast amounts of material into space at extreme velocities. Supernovae play a crucial role in cosmic evolution. The intense conditions during the explosion create many of the heaviest elements in the universe, including gold, uranium, and other metals. These elements are dispersed into the interstellar medium, becoming raw material for future generations of stars, planets, and eventually life. The explosion also compresses nearby gas clouds, often triggering new star formation. What remains after a supernova depends on the mass of the collapsed core. In some cases, it forms an ultra-dense neutron star, composed almost entirely of neutrons packed to extraordinary densities. In the most extreme cases, gravity overwhelms all known forms of pressure, and the core collapses into a black hole. These remnants represent the endpoints of massive stellar evolution. Stellar death is not an ending, but a transformation. Through mass loss, explosions, and compact remnants, dying stars reshape their surroundings and recycle matter back into the galaxy. This continuous cycle of birth, evolution, and death drives chemical enrichment and ensures that the universe grows progressively more complex over time. Supernovae are among the most energetic and influential events in the universe, marking the violent end of certain stars and profoundly shaping cosmic evolution. They occur when the internal balance of a star collapses catastrophically, releasing an immense burst of energy that briefly rivals the brightness of an entire galaxy. Beyond their dramatic appearance, supernovae are essential mechanisms for creating and distributing many of the elements that make up planets, living organisms, and the observable structures of the universe. There are two primary pathways to a supernova. One involves massive stars that have exhausted their nuclear fuel. As fusion progresses in such stars, increasingly heavier elements accumulate in the core until iron is produced. Iron fusion does not release energy, so once the core becomes dominated by iron, pressure support fails. Gravity causes the core to collapse in milliseconds, compressing matter to extreme densities. The collapse halts abruptly when nuclear forces resist further compression, producing a powerful rebound shock that tears the star apart in a core collapse supernova. The second major pathway involves compact stellar remnants known as white dwarfs. When a white dwarf exists in a close binary system, it can pull material from its companion star. As mass accumulates, density and temperature rise until runaway nuclear fusion ignites throughout the star. Because the white dwarf is supported by quantum pressure rather than fusion, this ignition cannot self-regulate. The result is a thermonuclear supernova that completely destroys the star, leaving no compact remnant behind. Both types of supernovae release extraordinary amounts of energy in a very short time. Temperatures during these explosions reach billions of degrees, and matter is subjected to intense pressures and neutron fluxes. Under these conditions, nuclear reactions occur that are impossible in normal stellar interiors. These reactions produce many of the elements heavier than iron, including gold, platinum, uranium, and other rare metals. Such elements require rapid neutron capture processes that only extreme environments like supernovae can provide. The material ejected by a supernova expands outward at thousands of kilometers per second, plowing into surrounding interstellar gas and dust. This expanding debris, known as a supernova remnant, carries newly synthesized elements into the galaxy. Over time, this material mixes with interstellar clouds, enriching them chemically. Future generations of stars form from this enriched gas, incorporating heavier elements into their composition. Planets that form around such stars inherit these elements, making rocky worlds and complex chemistry possible. Supernovae also play a regulatory role in star formation. The shock waves they generate compress nearby gas clouds, sometimes triggering the collapse of dense regions and initiating new star formation. At the same time, their intense radiation and kinetic energy can disperse gas, suppressing star formation in other regions. This dual influence helps shape the structure and evolution of galaxies, preventing them from converting all their gas into stars too quickly. On larger scales, supernova explosions influence galactic dynamics. Repeated explosions inject energy into the interstellar medium, driving large-scale flows of gas and contributing to galactic winds that can expel material from galaxies entirely. These processes are particularly important in smaller galaxies, where supernova feedback can significantly alter mass distribution and star formation history. Supernovae also serve as crucial tools for understanding the universe. Certain types exhibit remarkably consistent brightness, allowing them to be used as distance indicators across vast cosmic scales. Observations of these events have revealed key properties of cosmic expansion and provided evidence for the accelerating universe. In this way, supernovae connect stellar death to the largest questions in cosmology. Element formation through supernovae is central to the universe's increasing complexity. Without these explosions, the cosmos would be dominated by hydrogen and helium, lacking the raw materials needed for planets, atmospheres, oceans, and life. Every atom heavier than iron found on Earth was forged in extreme astrophysical events like supernovae, making these stellar deaths a direct link between the life cycles of stars and the physical foundations of existence. White dwarfs and neutron stars are compact stellar remnants formed when stars exhaust their nuclear fuel and can no longer sustain fusion in their cores. They represent two distinct outcomes of stellar evolution, determined primarily by the mass of the original star. Both objects are governed by extreme physics, where quantum mechanics and gravity dominate behavior in ways not encountered elsewhere as a natural consequence of star formation within dense regions of molecular clouds in interstellar space. When a portion of such a cloud collapses under its own gravity, it begins to rotate more rapidly due to conservation of angular momentum. The majority of the collapsing mass concentrates at the center, giving rise to a protostar, while the remaining material spreads out into a flattened, rotating structure known as a protoplanetary disk. This disk, composed primarily of gas, mostly hydrogen and helium and dust grains rich in heavier elements, serves as the birthplace of planets, moons, asteroids, and other small bodies. Within the protoplanetary disk, microscopic dust particles collide and stick together through electrostatic forces, forming larger aggregates. Over time, these aggregates grow into millimeter-sized grains, then centimeter and meter-scale objects, eventually becoming kilometer-sized bodies called planetesimals. Gravity becomes increasingly important at this stage, allowing planetesimals to attract nearby material and merge through repeated collisions. This process, known as accretion, leads to the formation of planetary embryos or protoplanets, which can range in size from small rocky bodies to objects comparable to Mars. The distribution of temperature and material within the disk strongly influences the types of planets that form. Close to the young star, high temperatures cause volatile substances such as water, methane, and ammonia to evaporate, leaving behind heavier elements like iron, silicon, and magnesium. As a result, planets forming in these inner regions tend to be rocky and dense. Farther from the star, beyond the so-called frost line, temperatures are low enough for ices to remain solid. This allows planetary cores to grow much larger by incorporating both rock and ice, eventually becoming massive enough to gravitationally capture large envelopes of hydrogen and helium, leading to the formation of gas giants and ice giants. Gas in the protoplanetary disk plays a crucial role not only in planet growth, but also in shaping planetary orbits. Interactions between forming planets and the surrounding gas can cause planets to migrate inward or outward from their original positions. This migration helps explain why some planetary systems contain massive planets extremely close to their host stars, a configuration not originally predicted by early models of planet formation. Over time, stellar radiation and winds disperse the remaining gas in the disk, typically within a few million years, effectively ending the era of giant planet formation. As the disk evolves, leftover debris that does not become part of planets remains as belts of asteroids, comets, and other small bodies. Collisions among these remnants can continue for hundreds of millions of years, reshaping planetary surfaces and delivering water and organic molecules to young planets. Moons may form through similar accretion processes within smaller disks around growing planets, or as a result of large impacts that eject material into orbit. The formation of planetary systems is therefore a complex, multi-stage process governed by gravity, angular momentum, temperature gradients, and disk dynamics. Observations of young stars with surrounding disks, along with the discovery of thousands of exoplanetary systems exhibiting a wide variety of architectures, show that while the basic mechanisms of planetary system formation are universal, the final outcomes can differ dramatically depending on initial conditions and evolutionary history. Planets are broadly classified based on their composition, structure, size, and location within a planetary system. The most fundamental distinction is between terrestrial planets and giant planets, a division that reflects differences in how and where these bodies form, as well as the materials from which they are made. This classification helps explain the diversity of planets observed both within our solar system and around other stars. Terrestrial planets are relatively small, dense bodies composed primarily of rock and metal. Their interiors typically consist of a metallic core, usually rich in iron and nickel, surrounded by a silicate mantle, and in many cases, a solid crust. These planets form in the inner regions of planetary systems, where high temperatures prevent light gases and volatile compounds from condensing. As a result, terrestrial planets have thin atmospheres or, in some cases, almost none at all. Surface features such as mountains, valleys, impact craters, and volcanic plains are common, shaped by geological processes including volcanism, tectonics, erosion, and impacts from smaller bodies. The density of terrestrial planets is relatively high because their mass is concentrated in heavy elements. This high density leads to strong surface gravity relative to their size, which influences atmospheric retention and geological activity. Heat generated from radioactive decay and residual energy from formation can drive internal processes such as mantle convection, which in turn may produce plate tectonics or volcanic activity. In some cases, molten cores generate magnetic fields that shield the planet from stellar radiation and help preserve its atmosphere. Giant planets, in contrast, are much larger and more massive, with compositions dominated by light elements and compounds. They form in the colder, outer regions of planetary systems, where ices and gases can remain stable during planet formation. Giant planets are generally divided into gas giants and ice giants, though both categories differ significantly from terrestrial worlds. Gas giants possess thick atmospheres primarily composed of hydrogen and helium, surrounding small, dense cores. Ice giants contain a higher proportion of heavier compounds such as water, ammonia, and methane, along with hydrogen and helium. Because of their large masses, giant planets exert strong gravitational influence on their surroundings. Their gravity allows them to retain extensive atmospheres and systems of rings and moons. Internally, these planets lack solid surfaces in the conventional sense. Instead, pressure increases gradually with depth, transitioning from gaseous outer layers to dense fluid or metallic states in the interior. Energy transport within giant planets often involves convection, leading to dynamic atmospheric patterns such as powerful storms, jet streams, and long-lived vortices. Atmospheres represent one of the most striking differences between terrestrial and giant planets. Terrestrial planet atmospheres, when present, are relatively thin and composed of heavier molecules such as nitrogen, carbon dioxide, and oxygen. Weather systems are driven by solar heating and interactions between the surface and atmosphere. On giant planets, atmospheres are deep, thick, and highly dynamic, with weather patterns extending thousands of kilometers below the visible cloud tops. These atmospheres play a major role in regulating internal heat loss and shaping observable features. Planetary classification also reflects orbital characteristics and evolutionary history. Some terrestrial planets may lose their atmospheres due to weak gravity or intense stellar radiation, while others may retain thick atmospheres through magnetic shielding or replenishment from volcanic outgassing. Giant planets may migrate significantly from their formation locations, altering the architecture of entire planetary systems and influencing the formation and survival of smaller planets. The distinction between terrestrial and giant planets provides a framework for understanding planetary diversity, but it is not absolute. Observations of planets around other stars reveal intermediate types with mixed characteristics, such as dense planets with thick atmospheres or low-density planets with substantial solid cores. These discoveries show that planetary types exist along a continuum shaped by formation conditions, composition, and long-term evolution, rather than fitting into perfectly rigid categories. Moons, rings, and minor bodies are integral components of planetary systems and provide crucial insight into their formation and long-term evolution. While planets dominate in mass and gravitational influence, these smaller companions record the history of accretion, collisions, and dynamical interactions that shape planetary environments over billions of years. Moons, also known as natural satellites, form through several distinct mechanisms. Some arise through co-accretion, forming from disks of gas and debris that surround young planets during their growth, in much the same way planets form around stars. Others originate through capture, when a planet's gravity traps a passing object into a stable orbit, a process that typically requires energy loss through interactions with gas or other bodies. A third and especially important mechanism involves giant impacts, in which a collision between a planet and a large body ejects material into orbit that later coalesces into one or more moons. The diversity of moon sizes, compositions, and orbital characteristics reflects these varied origins. Moons play a significant role in shaping planetary behavior. Large moons can stabilize a planet's axial tilt, reducing extreme variations in climate over long timescales. Gravitational interactions between a planet and its moons generate tidal forces that can heat interiors, drive volcanic or tectonic activity, and alter rotational periods. In some cases, tidal heating is sufficient to maintain subsurface oceans beneath icy crusts, demonstrating that moons can be geologically active worlds rather than inert companions. Ring systems consist of vast numbers of small particles orbiting a planet in a thin, flattened disk. These particles range in size from microscopic dust grains to chunks several meters across, and are typically composed of ice, rock, or a mixture of both. Rings are thought to form either from the breakup of a moon that ventured too close to a planet and was torn apart by tidal forces, or from leftover debris that never coalesced into a larger body. Although rings may appear permanent, Many are likely transient features on astronomical timescales, gradually evolving due to collisions, gravitational interactions, and the influence of planetary magnetic fields. The structure of rings is shaped by complex gravitational interactions. Embedded moons or nearby satellites can sculpt rings into sharply defined edges, gaps, and waves through resonant interactions. Collisions among ring particles redistribute energy and angular momentum, keeping the rings thin and dynamically active. Observations of ring systems provide valuable natural laboratories for studying disk dynamics, processes that also operate in protoplanetary disks and galaxies. Minor bodies include a wide range of small objects such as irregular moons, trojans, and debris populations that orbit planets or share their orbital paths. These bodies are remnants of planet formation that avoided incorporation into larger objects. Their compositions often preserve primitive material from the early stages of a planetary system, making them important records of chemical and physical conditions at the time of formation. Because they are small, minor bodies are strongly influenced by gravitational perturbations, leading to chaotic or evolving orbits. Interactions among moons, rings, and minor bodies can drive long-term changes in planetary systems. Orbital resonances can lock objects into repeating gravitational patterns, enhancing stability in some cases while causing instability in others. Collisions among minor bodies can generate new debris, replenish rings, or create temporary clouds of dust. Over geological timescales, these processes redistribute mass and energy, subtly reshaping the architecture of planetary systems. Together, moons, rings, and minor bodies reveal that planetary systems are not static arrangements of isolated planets, but dynamic, interconnected systems. Their existence highlights the importance of gravitational interactions, collisions, and tidal forces in planetary evolution, and demonstrates that even relatively small objects can exert a profound influence on the physical and environmental history of planets. Asteroids, comets, and meteoroids are small bodies that represent leftover material from the formation of planetary systems. Though modest in size compared to planets and moons, these objects are scientifically significant because they preserve primitive matter largely unchanged since the early stages of system formation. Their compositions, orbits, and interactions provide direct evidence of the processes that shaped planets and redistributed material across vast distances. Asteroids are primarily rocky or metallic objects that formed in regions of the protoplanetary disk, where material never fully accreted into a planet. They vary widely in size, from boulders only a few meters across to bodies hundreds of kilometers in diameter. Many asteroids are irregular in shape due to weak gravity and a history of collisions. Their internal structures range from solid monolithic rock to loosely bound, rubble piles, composed of fragments held together by gravity. These characteristics reflect repeated impacts and gravitational reaccumulation over billions of years. The composition of asteroids depends on their formation location and thermal history. Some are rich in metals such as iron and nickel, while others contain silicate minerals or carbon-rich compounds, including hydrated minerals and organic molecules. This diversity suggests that early planetary systems experienced strong temperature gradients and mixing processes. Asteroids are not static relics. Collisions among them continue to produce fragments and dust, gradually grinding larger bodies into smaller ones in a process known as collisional evolution. Comets differ from asteroids primarily in composition and origin. They form in the colder, outer regions of planetary systems, where volatile substances such as water ice, carbon dioxide, methane, and ammonia can remain solid. Comets typically consist of a mixture of ices, dust, and rocky material, often described as dirty ice. When a comet approaches a star, increasing temperatures cause its ices to sublimate, releasing gas and dust that form a surrounding cloud and extended tails. These features make comets highly dynamic and visibly active compared to most asteroids. The structure of a comet reflects its fragile nature. The nucleus is usually small and low in density, with weak internal cohesion. Gas released during sublimation can create jets that alter the comet's rotation and trajectory. Over repeated close passes to a star, comets lose mass and may fragment or become inactive, eventually resembling asteroids in appearance. This evolutionary connection shows that the boundary between asteroids and comets is not always sharply defined. Meteoroids are much smaller fragments, typically ranging from dust-sized particles to objects a few meters across. They originate from collisions between asteroids, the disintegration of comets, or debris ejected during impacts. When meteoroids enter a planet's atmosphere at high speed, frictional heating causes them to glow, producing meteors. If a fragment survives passage through the atmosphere and reaches the surface, it is called a meteorite. Meteorites provide direct physical samples of early planetary material and have been crucial for understanding planetary chemistry and age. The movement of asteroids, comets, and meteoroids is strongly influenced by gravitational interactions with planets. Resonances can concentrate or disperse these objects, altering their orbits over time. Some are deflected toward the inner regions of planetary systems, increasing the likelihood of impacts with planets and moons. Such impacts have played a major role in shaping planetary surfaces, delivering water and organic compounds, and occasionally causing mass extinctions. These small bodies collectively demonstrate that planetary systems remain dynamically active long after planet formation ends. Through collisions, orbital evolution, and material exchange, asteroids, comets, and meteoroids continue to influence planetary environments. They serve as enduring records of early system conditions and as agents of change that link the distant past of planetary formation with ongoing processes observed today. The solar system is a gravitationally bound collection of objects formed from the same rotating cloud of gas and dust, organized into a flattened, disk-like structure centered on a single star. Its overall architecture reflects the processes of angular momentum conservation, accretion, and long-term gravitational interaction. At the center lies the dominant mass, accounting for more than 99% of the total, while the remaining material is distributed among planets, moons, rings, and countless smaller bodies arranged in broadly stable orbital patterns. The planets are arranged in roughly circular, nearly coplanar orbits around the central star, a configuration inherited from the original protoplanetary disk. These orbits follow predictable paths governed by gravity, with orbital speed decreasing as distance from the center increases. The inner region of the system is compact and dominated by small, dense rocky planets, while the outer region is expansive and populated by massive planets with thick atmospheres and extensive satellite systems. This separation reflects the temperature gradient that existed during formation, which determined which materials could condense and accumulate at different distances. Between the planets lies a vast amount of empty space, punctuated by belts and populations of smaller objects. These regions are not random, but structured by resonances and long-term gravitational stability. Some zones are cleared of debris due to planetary influence, while others preserve ancient remnants of formation that never coalesced into larger bodies. The distribution of mass across the system is highly uneven, with planets occupying only a tiny fraction of the available volume, yet exerting a dominant influence over their surroundings. Orbital dynamics play a central role in maintaining the structure of the solar system. Each object follows an orbit defined by its distance, velocity, and gravitational interactions with other bodies. While these orbits are generally stable over long timescales, subtle perturbations can accumulate, leading to gradual changes in orbital shape or orientation. Resonant relationships, where orbital periods form simple ratios, can enhance stability or drive instability depending on the configuration. Such interactions explain gaps, clusters, and patterns observed among smaller bodies. The solar system is not static but evolves continuously. Collisions, tidal interactions, and the gradual loss of energy through radiation alter the system over billions of years. Impacts reshape planetary surfaces and generate debris, while gravitational encounters can scatter small bodies inward or outward. Some material is ejected entirely, while other material migrates inward and interacts with planets and moons. These ongoing processes mean that the current structure represents a snapshot in a long evolutionary sequence rather than a permanent arrangement. Beyond the major planets lies a vast outer domain where objects orbit at great distances, weakly bound by gravity. These distant regions act as reservoirs of icy bodies and preserve conditions closer to those present during the system's earliest history. Because gravitational influence weakens with distance, objects here are more susceptible to perturbations from passing stars or galactic tides, linking the solar system to its broader galactic environment. The structure of the solar system demonstrates how simple physical laws produce ordered complexity. Gravity organizes matter into stable orbits, angular momentum shapes the overall geometry, and time allows interactions to refine the system into its present form. Studying this structure reveals not only how the solar system came to be, but also provides a framework for understanding planetary systems throughout the universe. The Sun is a self-gravitating sphere of hot plasma that serves as the primary source of energy for the solar system and governs its overall stability through gravity. Its immense mass compresses material at its core to extreme temperatures and pressures, enabling nuclear fusion, the process that converts hydrogen into helium and releases vast amounts of energy. This energy flows outward through the Sun's interior and ultimately radiates into space as light and heat, sustaining planetary climates and driving nearly all physical and biological processes on nearby worlds. The internal structure of the Sun is organized into distinct layers, defined by how energy is transported. At the center lies the core, where temperatures exceed millions of degrees and fusion reactions occur continuously. Surrounding the core is the radiative zone, where energy moves outward slowly through the absorption and re-emission of photons by plasma particles. Beyond this region is the convective zone, where rising hot plasma and sinking cooler material transport energy more efficiently through bulk motion. These internal motions are not static. They evolve over time and play a key role in shaping the Sun's magnetic behavior. Above the visible surface lie the outer atmospheric layers, which transition from relatively cool to extremely hot over short distances. The photosphere is the layer from which most visible light escapes and is marked by granular patterns caused by convection beneath the surface. Above it lies the chromosphere, a region of rising temperature and dynamic motion, followed by the corona, an extended outer atmosphere that reaches temperatures far higher than the surface below. The extreme heat of the corona is linked to magnetic processes that transfer energy from the Sun's interior into its outer atmosphere. Solar activity arises from the interaction between plasma motion and magnetic fields generated within the Sun. Differential rotation, where different latitudes rotate at different rates, twists magnetic field lines and concentrates them into regions of intense magnetic strength. When these fields emerge at the surface, they suppress convection locally, producing dark regions known as sunspots. The number of sunspots varies in a roughly regular cycle lasting about a decade, reflecting the periodic reorganization of the Sun's magnetic field. More energetic manifestations of solar activity include flares and coronal mass ejections. Solar flares occur when stressed magnetic field lines suddenly reconnect, releasing enormous amounts of energy across the electromagnetic spectrum. Coronal mass ejections involve the expulsion of large clouds of magnetized plasma into space, When directed toward planets, these events can disturb magnetic fields, heat upper atmospheres, and interfere with technological systems. Such interactions demonstrate that solar activity extends far beyond the sun itself, influencing the space environment throughout the solar system. The sun also emits a continuous flow of charged particles known as the solar wind. This outflow fills interplanetary space and interacts with planetary magnetic fields and atmospheres. Magnetic fields can deflect much of this wind, creating protective regions that shield atmospheres from erosion, while planets lacking strong magnetic fields are more directly exposed. Over long periods, this interaction can significantly alter atmospheric composition and surface conditions. Although the sun appears stable on human timescales, it is slowly evolving. As fusion converts hydrogen into helium, conditions in the core gradually change, increasing energy output over billions of years. This long-term evolution affects planetary environments and sets ultimate limits on habitability. The sun's structure and activity therefore represent a balance between stability and change, providing a steady energy source while continuously shaping the dynamic space environment of the solar system. The inner planets are small, dense worlds that formed in the hot, inner region of the solar system, where intense temperatures prevented light gases and volatile compounds from condensing during planet formation. As a result, these planets are dominated by rock and metal, possess solid surfaces, and share broadly similar internal structures despite exhibiting very different surface environments and evolutionary histories. All inner planets have differentiated interiors, meaning heavier materials such as iron and nickel sank toward the center early in their history, forming metallic cores, while lighter silicate materials formed mantles and crusts. This differentiation was driven by heat from accretion, radioactive decay, and early impacts. The presence or absence of ongoing internal heat strongly influences geological activity, magnetic field generation, and surface renewal processes across these planets. Surface conditions among the inner planets vary dramatically due to differences in atmosphere, distance from the sun, rotation, and internal activity. Some possess thick atmospheres that trap heat efficiently, while others have thin or negligible atmospheres that allow surface temperatures to fluctuate widely. Without substantial atmospheres, impact craters remain preserved for billions of years, providing records of early solar system bombardment. In contrast, atmospheres and internal activity can erase or modify surface features through erosion, volcanism, or tectonic processes. Volcanism has played a central role in shaping interplanetary surfaces. Molten material rising from the mantle can flood large regions with lava, build volcanic mountains, and release gases that contribute to atmosphere formation. Over time, declining internal heat reduces volcanic activity, leading to geologically inactive surfaces. The timing and duration of volcanism vary among the inner planets, producing landscapes that range from heavily cratered terrains to smoother volcanic plains. Tectonic behavior also differs significantly. Some inner planets show evidence of surface deformation caused by internal stresses, such as fractures, ridges, and compressed crustal features. Plate tectonics, where the surface is divided into moving plates, is an especially effective mechanism for recycling crust and regulating atmospheric composition over long timescales. Where such processes are absent, planetary surfaces tend to become static, limiting long-term geological and climatic evolution. Magnetic fields provide another major point of contrast. Strong global magnetic fields are generated by the motion of electrically conductive material within molten planetary cores. These fields shield planets from charged particles emitted by the sun, reducing atmospheric loss and radiation exposure at the surface. Inner planets lacking active magnetic fields are more vulnerable to atmospheric erosion, especially during periods of intense solar activity in early early system history, water and other volatiles represent a key factor in determining planetary environments. Some inner planets show clear evidence of past or present interactions with water, such as erosion features or mineral alterations, suggesting that liquid water once played a role in shaping their surfaces. Others are extremely dry, either because they never acquired significant water or because it was lost over time due to atmospheric escape or chemical processes. The presence or absence of water has profound implications for surface chemistry, geology, and potential habitability. Together, the characteristics of the inner planets illustrate how small differences in initial conditions and subsequent evolution can produce vastly different outcomes. Despite forming from similar materials in the same region of the solar system, variations in mass, atmosphere, internal heat, and magnetic protection have led to a wide range of physical environments, offering valuable insight into how rocky planets evolve both within and beyond the solar system. The outer planets occupy the cold, distant regions of the solar system and differ fundamentally from the inner rocky worlds in both composition and structure. Formed beyond the frost line, where temperatures were low enough for ices to condense, these planets accumulated large amounts of volatile material during their formation. Their massive sizes and strong gravitational fields allowed them to retain thick atmospheres and extensive systems of moons and rings, making them dominant influences in the outer solar system. Unlike the inner planets, the outer planets do not possess solid surfaces in the traditional sense. Their visible layers consist of deep atmospheres composed primarily of light gases mixed with heavier compounds, beneath which pressure and temperature increase continuously with depth. In their interiors, materials transition from gaseous to liquid, and under extreme conditions, to exotic states of matter. Energy transport within these planets is largely driven by convection, resulting in complex atmospheric circulation patterns, powerful winds, and long-lived storms. The gravitational dominance of the outer planets shapes the architecture of the solar system. Their strong influence governs the orbits of nearby moons, rings, and smaller bodies, while also affecting distant populations of icy objects. By scattering or capturing debris during the early stages of planetary formation, the outer planets played a key role in determining which material was incorporated into planets and which remained as remnants. Their interactions continue to regulate the flow of comets and other small bodies toward the inner solar system. Beyond the outer planets lies the Kuiper Belt, a vast, disc-shaped region populated by icy objects that orbit the Sun at great distances. These bodies are remnants of the original protoplanetary disk that never accreted into a planet, preserved by the cold and relative isolation of the outer solar system. Kuiper Belt objects vary widely in size, from small fragments to bodies large enough to be nearly spherical, and many contain mixtures of ice, rock, and organic compounds. The Kuiper Belt represents a transitional zone between the planet-dominated region of the solar system and its distant outskirts. Gravitational interactions, particularly with the outer planets, shape the distribution and orbits of Kuiper Belt objects. Some are locked in stable resonances that protect them from close encounters, while others have more chaotic paths that can be altered over time. These interactions can send icy bodies inward, where they may become active comets when exposed to increasing solar heat. The outer solar system is also a reservoir of information about early planetary conditions. Because temperatures remain low and solar radiation is weak, many objects here have undergone minimal alteration since their formation. Their compositions preserve records of the chemical environment that existed during the earliest stages of the solar system. Studying these distant bodies provides insight into how volatile compounds were distributed and how complex molecules may have been delivered to the inner planets. Together, the outer planets and the Kuiper Belt demonstrate the large-scale organization of the solar system beyond the realm of rocky worlds. Massive planets act as gravitational architects, while distant icy populations preserve primordial material and supply a continuing source of small bodies. This region highlights the balance between stability and dynamism that characterizes the solar system as a whole, showing how distant objects remain connected to planetary evolution through gravity and time. The interstellar medium is the vast, diffuse collection of gas, dust, and energetic particles that fills the space between stars within a galaxy. Although extremely tenuous by everyday standards, it contains enough material to play a central role in galactic evolution, star formation, and the propagation of radiation across cosmic distances. This medium is not uniform but structured into regions that differ widely in temperature, density, composition, and ionization state. Gas in the interstellar medium exists primarily as hydrogen, with smaller amounts of helium and trace quantities of heavier elements produced by stellar nucleosynthesis. Depending on local conditions, this gas may be cold and neutral, warm and partially ionized, or extremely hot and fully ionized. Cold, dense regions allow atoms to combine into molecules, forming molecular clouds that serve as the birthplaces of new stars. In contrast, hot ionized regions are often created by supernova explosions and energetic stellar winds, injecting energy and heavy elements back into the surrounding environment. Dust grains make up only a small fraction of the interstellar medium's mass, but have a disproportionate influence on its behavior. These microscopic particles, composed of silicates, carbon compounds, and ices, absorb and scatter light, shaping how galaxies appear at different wavelengths. Dust also provides surfaces on which chemical reactions can occur, enabling the formation of complex molecules that would otherwise be inefficient in the gas phase. Over time, dust grains are both created and destroyed by stellar processes, linking them directly to cycles of star birth and death. Cosmic radiation permeates the interstellar medium in the form of high-energy particles and electromagnetic waves. Cosmic rays, which consist mainly of fast-moving protons and atomic nuclei, are accelerated by energetic events such as supernova shocks. As they travel through space, they interact with gas and magnetic fields, influencing chemical reactions and contributing to the ionization of otherwise neutral regions. Electromagnetic radiation, ranging from radio waves to gamma rays, carries information about distant sources and modifies the physical state of interstellar material. Magnetic fields thread through the interstellar medium and play a crucial role in shaping its structure and dynamics. Though weak, these fields can influence the motion of charged particles, regulate the collapse of gas clouds, and guide the flow of cosmic rays. Interactions between magnetic fields and turbulence create complex filamentary structures within gas clouds, affecting when and where star formation occurs. The balance between gravity, thermal pressure, turbulence, and magnetic forces determines the long-term evolution of interstellar regions. The interstellar medium is far from static. Energy input from stars continuously stirs and reshapes it, while gravity draws material together into denser concentrations. Shock waves from stellar explosions compress gas, triggering new generations of star formation, while intense radiation from massive stars can erode surrounding clouds and halt further collapse. This feedback creates a self-regulating cycle in which stars both arise from and transform the medium around them. Cosmic radiation and interstellar matter also interact with planetary systems. As stars and their planets orbit through the galaxy, they move through varying interstellar environments that can influence the outer boundaries of stellar systems. Over very long timescales, changes in cosmic radiation exposure and interstellar density may subtly affect planetary atmospheres and surface conditions. Together, the interstellar medium and cosmic radiation form the connective tissue of a galaxy. They link individual stars into a larger system, recycle material across generations of stellar evolution, and regulate the physical and chemical conditions of space. Understanding this environment is essential for explaining how galaxies evolve, how stars and planets form, and how energy and matter are distributed on the largest scales. Spacetime and gravity are inseparable concepts that describe how matter, energy, and motion are organized in the universe. Rather than viewing space and time as independent, fixed backgrounds, modern physics treats them as a single, interconnected fabric whose geometry is shaped by the presence of mass and energy. Gravity is not simply a force acting at a distance, but a manifestation of how this space-time fabric bends and evolves. In this framework, massive objects alter the structure of space-time around them. Planets, stars, and galaxies curve the surrounding geometry, and other objects move along paths determined by this curvature. What appears as gravitational attraction is, in reality, motion along the straightest possible paths within a curved space-time. This interpretation explains why objects fall toward massive bodies and why planetary orbits follow predictable trajectories without requiring a traditional force pulling them inward. Time itself is affected by gravity and motion. Clocks in strong gravitational fields tick more slowly than clocks farther away, and clocks moving at high speeds run slower than those at rest relative to an observer. These effects, though subtle under everyday conditions, become significant near massive objects or at velocities approaching the speed of light. Time dilation demonstrates that time is not absolute, but depends on the observer's position and motion within space-time. The geometry of space-time also determines how light travels. Light follows curved paths when passing near massive objects, an effect known as gravitational lensing. This bending can magnify, distort, or multiply the images of distant objects, providing powerful evidence that space-time curvature is real. Because light always travels at a constant speed locally, its apparent bending arises from the geometry of the space through which it moves, not from changes in its intrinsic speed. Gravity influences not only motion, but also the flow of energy and the evolution of cosmic structures. Regions of slightly higher density in the early universe produced small distortions in space-time that attracted additional matter, growing into stars, galaxies, and clusters. Over cosmic time, gravity has amplified tiny initial irregularities into the large-scale structure observed today. This process links the behavior of space-time on the smallest scales to the distribution of matter across billions of light years. Extreme gravitational environments reveal the most dramatic consequences of space-time curvature. Near very compact objects, curvature becomes so strong that familiar notions of distance and time break down. Paths that once led outward may bend inward, and time for distant observers appears to slow dramatically near such regions. These extremes test the limits of current physical theories and provide insight into how gravity behaves under conditions far beyond those found on planets or stars. Gravity also affects the propagation of disturbances in space-time itself. When massive objects accelerate, especially during violent events, they can produce ripples that travel outward at the speed of light. These distortions carry energy and information about their sources, showing that space-time is dynamic rather than rigid. The detection of such effects confirms that gravity is not instantaneous, but propagates through the universe. On large scales, the structure of space-time determines the overall behavior of the universe. The expansion of space is governed by the balance between mass, energy, and the geometry of the cosmos. Depending on these factors, expansion can slow, accelerate, or change character over time. Gravity thus shapes not only local motion but the ultimate fate of cosmic evolution. Space-time and gravity together provide a unified description of motion, energy, and structure. They replace the idea of an unchanging stage with a responsive, evolving framework in which matter and geometry continuously influence one another. This perspective underlies modern cosmology and astrophysics, offering a coherent explanation for phenomena ranging from falling objects to the behavior of the universe as a whole. Space weather refers to the changing physical conditions in space, driven primarily by activity from a star and its interaction with surrounding planetary environments. These conditions arise from the continuous outflow of energy, radiation, and charged particles, and they can vary over timescales ranging from minutes to decades. Although space may appear empty, it is an active environment where electromagnetic fields and energetic particles interact in complex and sometimes disruptive ways. The primary driver of space weather is stellar activity. A star emits not only light and heat, but also streams of charged particles and bursts of electromagnetic radiation. Sudden releases of energy can inject vast quantities of high-energy particles into space, dramatically altering the local environment. These disturbances propagate outward through space, carried by stellar winds and magnetic fields, and can reach planets orbiting far from the source. When energetic particles and magnetic disturbances encounter a planet, their effects depend strongly on the planet's magnetic field and atmosphere. A strong magnetic field can deflect many charged particles, guiding them along magnetic field lines toward the polar regions. Their interactions with atmospheric gases produce luminous phenomena and localized heating. In contrast, planets with weak or absent magnetic fields are more directly exposed, allowing charged particles to penetrate deeper into the atmosphere and interact with surface materials. Space weather can significantly influence planetary atmospheres over long periods. Repeated exposure to energetic particles and intense radiation can strip away atmospheric gases, especially lighter elements, through processes such as sputtering and thermal escape. Early in a planetary system's history, when stellar activity is often more intense, these effects can permanently alter atmospheric composition and density. Over billions of years, such interactions help determine whether a planet retains a thick atmosphere or becomes thin and dry. Technological systems are particularly sensitive to space weather effects. Charged particles and fluctuating magnetic fields can induce electrical currents, disrupt communication signals, and damage electronic components. Satellites operating beyond the protection of Earth's atmosphere are especially vulnerable to radiation, which can degrade materials and interfere with onboard systems. Navigation, communication, and power infrastructure can all be affected when strong space weather events occur. Space weather also poses risks to biological systems. Increased radiation exposure can be harmful to living tissue, making it a concern for astronauts and future human exploration beyond protective planetary environments. Even at the surface of planets, enhanced radiation levels during extreme events can temporarily increase exposure, though thick atmospheres and magnetic fields provide substantial shielding. Understanding space weather is therefore essential for assessing long-term habitability and planning safe exploration. The space environment is shaped by ongoing interactions between stellar output and the interplanetary medium. Magnetic fields carried by stellar winds interact with planetary magnetic fields, creating complex boundary regions where energy is transferred and particles are accelerated. These interactions are dynamic, responding continuously to changes in stellar activity and planetary motion. As a result, space weather is not a constant background condition, but a fluctuating system with periods of relative calm and intense disturbance. Studying space weather reveals that planets are not isolated objects, but participants in a larger, active space environment. The effects of stellar activity link stars directly to planetary evolution, atmospheric stability, and technological vulnerability. By understanding how space weather operates and how its effects propagate, scientists gain insight into both the challenges of living in space and the long-term processes that shape planetary systems across the universe. Observational astronomy is the practice of gathering information about the universe by detecting and analyzing radiation emitted or reflected by celestial objects. Because most cosmic objects cannot be reached directly, telescopes serve as extensions of human senses, collecting faint signals across vast distances and converting them into measurable data. The design and placement of telescopes determine what portions of the universe can be studied and how clearly its structures and processes can be resolved. Telescopes operate by collecting electromagnetic radiation and focusing it for analysis. The most familiar instruments detect visible light, but modern astronomy relies on observations across the entire electromagnetic spectrum. Radio waves, infrared radiation, visible light, ultraviolet radiation, X-rays, and gamma rays each reveal different physical processes. Cooler objects emit strongly at longer wavelengths, while extremely energetic phenomena produce high-energy radiation. Observing across multiple wavelengths provides a more complete picture than any single band alone. Ground-based telescopes are limited by Earth's atmosphere, which absorbs or distorts many forms of radiation. Atmospheric turbulence blurs images, reducing resolution, while gases block most ultraviolet, X-ray, and gamma-ray radiation entirely. To overcome these limitations, astronomers use adaptive optics systems that compensate for atmospheric distortion in real time, as well as telescopes placed at high altitudes and dry locations where atmospheric interference is minimized. Space-based telescopes avoid atmospheric effects altogether by operating above Earth's atmosphere. These instruments can observe wavelengths that never reach the ground and can achieve exceptionally stable, high-resolution measurements. However, space telescopes face strict constraints on size, maintenance, and lifespan, making their design and deployment technically demanding. Ground and space-based observatories therefore complement one another, each filling gaps left by the other. Different telescope designs are optimized for different wavelengths and scientific goals. Reflecting telescopes use mirrors to collect and focus light, allowing for large apertures that increase light-gathering power. Radio telescopes employ dish-shaped antennas to detect long-wavelength signals, often working together in large arrays that function as a single, much larger instrument. Interferometry, which combines signals from multiple telescopes, dramatically improves resolution and enables detailed imaging of distant objects. Telescopes do not simply produce images, they generate data that must be carefully processed and interpreted. Spectroscopy separates incoming light into its component wavelengths, revealing chemical composition, temperature, motion, and magnetic properties. Precise measurements of brightness over time allow astronomers to detect variability, such as pulsations, eclipses, or explosive events. By analyzing these signals, scientists infer properties that cannot be directly observed. Observational astronomy is shaped by technological progress. Advances in detectors, computing power, and data analysis methods have transformed astronomy into a data-rich science. Modern surveys can catalog millions or even billions of objects, mapping large portions of the sky in unprecedented detail. Automated pipelines and statistical techniques are essential for extracting meaningful patterns from these vast datasets. The interpretation of observations depends on careful calibration and error analysis. Instruments introduce biases and noise that must be understood to avoid false conclusions. Observations are often repeated and compared across different instruments and wavelengths to confirm results. This emphasis on verification ensures that conclusions about distant and unobservable phenomena remain scientifically robust. Through telescopes and observational techniques, astronomy connects theoretical models with physical reality. Observations test predictions, reveal unexpected phenomena, and drive the refinement of scientific understanding. By capturing light that has traveled for millions or billions of years, telescopes allow humanity to study not only distant places, but also the deep history of the universe itself.